Students, good morning. Today we are going to see asynchronous checkpointing and recovery algorithm. What's the concept of algorithm? This algorithm is based on asynchronous checkpointing. So what is asynchronous checkpointing? Asynchronous checkpointing means there is no cooperation between the process. Okay. In synchronous checkpointing, all processes are cooperating and waiting for a time. There is a control over the processes. But here in asynchronous, there is no control. Okay. That's asynchronous. Okay. The main concept of this algorithm is to find a consistent set of checkpoints from which a system can be recovered in case of failure. So what is a consistent set of checkpoints? Consistent set of checkpoints means here, while the checkpoints are taken, the sources of all messages should be inside the inside the cut. Okay. But in receiving end, the receiving end may be outside the cut or right side of the cut line, inside the cut or left side of the cut line. The cut line can be taken such that the sources of all messages should be inside the cut or left side of the cut. Okay. If the sources of messages are outside the cut or right side of the cut, then it will be an inconsistent cut. See the diagram. The red points are checkpoints. See the first diagram. Two messages are being sent from messages are being sent from the process P1 to P2. The source of messages are inside the cut line, inside the cut line or left side of cut line. So it can be consistent one. See the next diagram. The last message. If you see the source of event, it is right side of the cut line, right side or outside of the cut line. So it is a inconsistent cut. So the checkpoint should be taken such that the line should be a consistent one. Okay. So each process maintains a set of messages it gets sent to all other processes and also maintains the number of messages it gets received from other processes. Okay. Then assumptions of algorithm: communication channels are reliable, messages are delivered in first order. Let us assume the communication channels are reliable, first order. Okay. Infinite purpose. Transmission delay is arbitrary. Arbitrary means the delay may be a short delay or long delay, but number of the transmission delay is finite, but the duration may be a short or long. Computations. Whenever an event is triggered, the triplet should be recorded. It's like a record and it should be recorded. And the format of triplet is triplet within bracket m, s, message sent. This is the format of the triplet. Okay. So once the message is being sent from one process to another process, the state of the process also be changed. For example, let us take the two processes P1 and P2. See the diagram. There are two processes P1 and P2. First, the process is at the state yes. Okay. Now it has sent one message to the process P2. So the status of the process yes is changed to S dash. Okay. Similarly, the status of the process B2 also changed to S dash. Okay. See the diagram. Types of logs. Two types of logs are used in this algorithm. There are volatile and stable log. Volatile log means the log content will be lost if the process crashes. In case of any crashes due to some network failure or any other reason, the content of the log will be lost. Stable means the content will be stable. Even the process crashes, the content are stable. That means we can recover the content from the stable log. Stable or non-volatile. Asynchronous checkpointing I already told. There is no cooperation between the process. There is no control over the process. That is asynchronous. Okay. While taking checkpointing, the checkpoint is taken with no cooperation between the process. Each process will take their own checkpoints. Okay, each process will take their own checkpoints. While taking checkpoints, no, the process will not communicate with each other to take the checkpoint. Each process will take their own checkpoints. So the checkpoints are asynchronous. There is no synchronization in taking checkpoints. Okay. So the triplets are recorded without any synchronization with other processes. Notations: send I to J. I to J means process 1 to process 2. Okay, number of messages sent by process Pi to Pj from the beginning of computation to checkpoint. We are going to take checkpoint, and how it should the checkpoint should be taken. Before the checkpoint, how many messages are being sent from the process, source process to destination process? That messages should be recorded. Similarly, receiving end, how many messages are received from the source process to receiving process before the checkpoint? It's a formula. Okay. Notations. And this is the juan-venkatesan algorithm. Just go through the algorithm. I'll explain the algorithm in stepwise, step A and step B. Let us take the step A of the algorithm. If the process B is recovered after a failure, then checkpoint equal to latest event log in the stable storage. Okay. Now assume the process is recovered from the failure, so it has to continue the process. From where it can be continued? From the latest checkpoint that is being recorded in the stable storage, not in the volatile storage. Okay. Or else, if process B is recovering after failure, then else, if there is no failure or no requirements, as usual, let us continue. Checkpoint will latest event took place in Pi. It may be either volatile storage or in non-volatile storage. Most probably, in case if nothing is happened, it will continue the process, take checkpoints from the volatile storage only. Okay. And if see the diagram, there are 4 checkpoints: checkpoint 1, checkpoint 2, checkpoint 3, and checkpoint 4. Okay. A failure occurred at that point, and after some time, the process recovered from the failure. So we'll go to the checkpoint. It is recorded in the stable storage. See, checkpoint 3 is recorded in stable. Okay, stable storage. Checkpoint 4 is recorded in volatile storage. Now it has to take only it has to take the checkpoint from the stable storage, not from the volatile storage. So which one is stored in stable? Checkpoint 3. Checkpoint 4 is stored only in volatile. So it will go to checkpoint 3 and recover the process from checkpoint 3, not checkpoint 4. Okay. See the diagram. Now assume there are 3 processes are running X, Y, and Z. Okay. 3 processes X, Y, and Z are running. And X1, X2, X3, X4, X5, X6 are the events happened in the process X. Now take the process Y. Y1, Y2, Y3, Y4, Y5, Y6. These are the events happened in process Y. And take the process Z. There are only 2 events are happening, Z1 and Z2. Okay. Now see the messages. What are the messages coming from X to Y? See the message M1, M3, M4. These 3 messages are being sent by X to the process Y. And X send the message M2 to Z. There is one message is being transferred from the process X to Z. And there are two messages are sent by the process Y to X. There are N1 and N2. That's shown in red line. See the red line, N1, see the messages in red line, N1 and N2. These two messages are sent by process Y. And message M1, M3, M4 are the messages sent by process X to Y. And M2 is the message sent by the process X to the process Z. Okay. And see the messages O1 and O2. O1 and O2 are orphan messages. O1 message is received by the process Y, and the message O2 is received by the process Z, but the source of the process messages O1 and O2 are unknown. We don't know the source of the process message, source of the message O1 and O2. Oh, the messages O1 and O2 are being received by the process Y and X, but who is the source of the messages O1 and O2? We don't know. So these messages are called orphan message. Okay. So as per the set diagram, message sent by P1 to P2 are 3. P1 to P2 are X to Y are 3. And message sent by P1 to P3, that is X to Z is 1. And message sent by P2 to P1, that is Y to X is 2. Message sent by P3 to other processes is null. That is Z to other processes is null. Assume P1, P2, P3 are X, Y, and Z. Okay, all same. Either P1, P2, P3 are X, Y, and Z. Okay. So message sent by P3 to other process is null. That is message sent by the process Z to other process is null. Messages O1 and O2 are orphan messages. That is sender is unknown. Okay. Can you understand what I'm saying? See the algorithm. Take the step A. Take the step A of the algorithm. For k equal to 1 to n, that is n is the number of processes in the system. Do outer loop. Then come in inner loop. For each neighboring process Pj, do compute send I to j, send a rollback message to send a rollback message. The format of rollback message is rollback I comma send I to j checkpoint message to p of j. What is this algorithm? Let us see. Take that algorithm. For each neighboring process p of j, do compute send I to j checkpoint I, right? So take k equal to 1. What is k equal to 1 means? I equal to 1. For I equal to 1, what are the neighboring processes? The neighboring processes are Y and Z, or J2 and J3. Either J2 and J3 are neighboring process to the process J1, or we can say the neighboring process to the process X are Y and Z. Okay. How many messages are being sent from I to J? That is X to Y. That is process 1 to process 2. Answer is 3. 3 messages are being sent from the process X to Y. They are M1, M3, and M4. Okay. Okay. Let us see the diagram. Only 3 messages are sent from X to Y. M1, M3, and M4. Carefully see the diagram. You can understand. See the diagram. How many messages are sent from X to Y? 3, M1, M3, and M4. So we are computing how many messages are being sent from I to J. Now, when k equal to 1, compute I to J up to the checkpoint I. Okay. So send 1 to 2. How many messages? 3. So the number of messages sent from X to Y is 3, M1, M2, and M3. Send 1 to 3. How many messages are sent from the process 1 to 3? That is process X to Y, X to Z. X to Z is, that is also X to Z is 1, right? So number of messages sent from X to Z is 1. That is the message M2. Message M2 is the only message sent by the process X to Z. Okay. Do you understand? Now let us see how how to send the rollback message. This is the algorithm for sending rollback messages. See the algorithm. Now let us see how the rollback messages are being sent. If received J to I. So if you read J to I, arrow, see the arrow mark. J to I means J is the receiving end, I is the sourcing end. Okay. I is the origination of message, and Z is the J is the receiving end. Okay. E greater than C. What is C? C indicates the actual number of messages received before the last checkpoint. Okay. So at this checkpoint, how many messages J actually received from I? That is, how many messages Y actually received from X? Answer is 3. M1, M3, M4, right? Only 3. So C equal to 3. So C equal to 3. But one more message O1 is also being received by Y after the checkpoint. Okay, that has happened. Unknowingly, one offer message is also being received by the process Y. So Y received one more offer message. So 3 plus 1 equal to 4. So now the process Y received 4 messages. Out of 4 messages, 3 messages sent by X. One more offer message is also received, but the source of the offer message is unknown. Okay, so actually Y received 4 messages. So received I to J up to this checkpoint, greater than C. So 4 greater than C. 4 is greater than C, true. That is not less than, and there should be a greater than. That is a mistake in that, greater than. So 4 is greater than 3, right? 2, right? So now come here. Find the latest event E such that receive I to J of event equal to C. So now we are going to find the checkpoint at which the number of messages received by Y is equal it should be equal. Okay. Now we are going to find the event at that point. The number of messages sent by the source process X is equal to the number of messages received by the process at the checkpoint. Okay. So number of received events that happen at Y at this moment is only 3, not 4. That is, the last event saved in volatile memory is Y4. Okay. Here, take the events happen in Y. What are the events happen in Y? Y1, Y2, Y3, Y4, Y5, Y6. So at the point here, after Y4, we have taken on checkpoint. See the diagram. After the event Y4, we have taken on checkpoint. At this checkpoint, the number of messages sent by the process X is equal to number of messages received by the process Y. Okay, at this checkpoint, the number of messages sent by X is equal to number of messages received by the process Y. Okay, this is the checkpoint where the both sending message and receiving message equal. So ignore the orphan message even and change the checkpoint to the previous one. So now change the checkpoint to the checkpoint at Y4. Okay, now the checkpoint has been changed consistently. Okay, do you understand? Now at that checkpoint, the number of messages sent and the number of messages received are equal. So change the checkpoint to Y4. Then only the checkpoint will be consistent one. Okay, do you understand what I'm saying? Now I equal to 1, J equal to 3. So J becomes 3 now. The loop is running, right? So that means X2 Z. Okay, the loop is changed from X to Y to X to Z. The number of messages received by Z from X is only 1. So equal to C equal to 1. But one more orphan message also occurred. So received of Z from I becomes 2. So 2 greater than 1. So 2 is greater than 1. True. So change the checkpoint to the event which is lastly saved in volatile message. Change checkpoint to Z1. So Z1 is the event, and that checkpoint may be a consistent one because that is recorded in volatile. Similarly, take the process Y4. At the process Y4, at the event Y4, both receiving and both sending and receiving message equal, and the event Y4 is recorded in volatile, non-volatile storage also. The event Y4, assume the event Y4 is recorded in non-volatile. So we have moved the checkpoints to Y4. Similarly, here also Z1 is the event. What's that event? Receiving event, Z1. And we have taken a checkpoint there. So change the checkpoint from O2 to Z1. It will be consistent. Z1 is recorded in non-volatile also. We change checkpoint from Z2 to Z1, then it will be consistent one. Okay. Here we are moving the checkpoints to consistent place. We are moving the checkpoint to consistent place so that if you take the cut, it will be a consistent cut. Okay. So loop first to outer loop K1 is over. So we can go to the second loop K equal to 2. K to 2 means 2 to 1. So message sent by Y. Now we have moved to process Y. Okay. Now we are going to compute how many messages sent by the process Y to X, and we are going to compute how many messages the process Y sent to Z. Okay. Now the process Y sent 2 messages to the process X. What are the messages? N1 and N2. See the diagram. The messages are indicated in red color. See the red color messages N1 and N2. So 2 messages are sent by the process Y to X. So message N1 and N2 are sent by Y to X. No orphan message here. No orphan messages are sent from. So no orphan messages are received by the process X. Okay. So C equal to 2 and received also equal to 2. Both are same. 2 greater than 2 false. So no changes in checkpoint, no rollback. Similarly, send 2 to 3, that is Y to Z. Process Y not send any message to Z. So no changes. This loop is also K equal to is also over. So we can go to next loop. K equal to 3. Compute I to J up to the checkpoint, latest checkpoint. 3 to 1, that is Z to X, no messages. Then 3 to 2, that is Z to Y, no messages. So no messages are being sent from Z to anywhere. So no need for rollback. Now the loop is over and the control will come out of the program. The checkpoints can be moved to consistent points. Now, if the cut is taken, then it may be a consistent one. So now if you change cut is taken, see, ignore the previous cut. Now take the new cut. The new cut is like that. See the diagram. The new cut line is, see the black color line, the cut line. See the diagram. See the diagram. In this diagram, all the sources of messages are inside the cut line. Okay. Our sources of messages are inside the cut line, that is left side to the cut line. So this cut line is a consistent one. And since the cut line is consistent one, the local snapshot is consistent one. And since the local snapshot is consistent one, if you take the global snapshot also a consistent one. Everything will be consistent one. Checkpoint is consistent, local snapshot is consistent, and global snapshot also consistent one. So this algorithm is helpful to take the local checkpoints, and so that the global snapshot and the global snapshots are consistent one. Okay. Thank you. So I'll give you an example for the John-Venkatesan algorithm in the next class. Okay. Thank you.